Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Have you ever, just stood outside on a really clear night, stared up at the sky, and wondered if the way all those stars are laid out is just a random roll of the dice?
I think it's a supernatural human instinct. It looks so chaotic up there.
Right. It feels like this totally random scattering of light. And honestly, for the better part of a century, that was basically the scientific consensus, wasn't it?
Yeah, pretty much.
Yeah.
The prevailing assumption in astrophysics has always been that the universe, at least at its most fundamental level of creating things, operates like a massive casino.
A cosmic lottery.
Exactly, a cosmic lottery. If you look at how stars are born inside these giant molecular gas clouds, the idea was always that we were basically witnessing totally random chance.
Like turbulence or just random quantum fluctuations dictating whether a pocket of gas becomes a tiny little star or a huge, bright giant.
Right, just completely stochastic.
Right.
Meaning, random.
Well, today we are going to completely tear that assumption apart, because we're exploring this huge fundamental shift in how we understand the cosmos.
It really is a massive paradigm shift.
Yeah, thanks to some recent breakthroughs, specifically from astrophysicists at Nanjing University and the University of Bonn, we are finding out that star formation is actually not a lottery at all.
Not even close. It turns out there is a highly efficient, self-regulating mathematical order running the whole show.
Okay, let's unpack this, because to really grasp why this hidden blueprint is so mind-blowing, we first need to look at the factories themselves, right? The nurseries where these stars are born.
Yeah, we have to establish the baseline because we aren't talking about empty space here.
Yeah.
Stars form in these incredibly violent, complex environments called giant molecular clouds.
And these things are just monstrous.
Well, absolutely monstrous.
Yeah.
We're talking about clouds of gas and dust that can be hundreds of light years across.
Wow.
And they contain hundreds of thousands, sometimes millions, of times the mass of our own sun.
So inside these massive clouds, you have gravity trying to pull everything together.
Right. Gravity is constantly trying to collapse the gas in on itself, but it's fighting against the outward thermal pressure of the gas, plus magnetic fields and just supersonic turbulence running through the whole cloud.
It sounds like an absolute war zone.
It really is. And for a star to actually form, gravity has to win that battle in a specific spot.
Okay, and the traditional view was that where gravity won and how much gas it managed to pull in before a star ignited was just totally random.
Exactly, just chaotic local variables. If a random eddy in the gas happened to push a bit more material together, boom, you got a slightly bigger star.
But the products coming off this cosmic assembly line are insanely different. Like, you look at a new star cluster and it's not just a uniform batch of clones.
No, you see wild extremes.
Yeah.
On the lower end, you have these small, cool, dim stars, the M dwarfs.
Right, which are basically well, my favorite analogy for these is reliable, low-wattage LED nightlight.
I like that.
You plug it in, it barely uses any power, and it just lasts forever.
Pretty much. They operate super conservatively. A low-mass star mixes its fuel really efficiently and burns it at a very low temperature. So theoretically, it can live for trillions of years.
Trillions. But then, coming out of the exact same gas cloud, you have these absolute monsters, the O-type giants.
The massive ones, yeah.
These are like lighting a stick of dynamite. They can be up to 10 times the mass of our sun, right?
Up to 10, sometimes 20, or even higher.
And they are blindingly bright, like 100,000 times brighter than our sun.
Yeah, because the relationship between a star's mass and its brightness isn't a straight line. It's exponential.
Wait, really? So 10 times the mass doesn't just mean 10 times the brightness?
No, not at all. Because of the immense gravity crushing down on the core of a massive star, it has to burn its fuel exponentially faster just to push back and keep from collapsing under its own weight.
So it's running a much hotter, much more aggressive engine.
Exactly. And the consequence of running that ultra-high-performance engine is that it burns through its fuel incredibly fast. A massive star might only live for a few million years.
Over in a flash. Dynamites versus nightlights.
Right. So mass isn't just about physical size. It dictates the entire life cycle, the energy output, and the death of the star.
So here is the million-dollar question for you. If they're all coming from the exact same vast gas cloud, How do we end up with such wildly different products at the end of the assembly line?
Well, to answer that, we have to look past the individual stars and look at the galaxies themselves. The size of the factory dictates what can come off the line.
Right, so let's do a tale of two galaxies here. Let's compare a dwarf galaxy with a massive elliptical galaxy.
Okay, so a dwarf galaxy has a relatively low total mass. It just doesn't have as much gas and dark matter to work with.
So its molecular clouds are smaller?
Right, and because of that strict environmental limit, a dwarf galaxy will not, and actually cannot, produce any extremely massive stars.
Wait, none at all.
None. The overall gravitational environment is too shallow. You won't find a single ultra-bright, massive O-type star being born in a dwarf galaxy.
Okay, but contrast that with a massive elliptical galaxy, especially in the early universe. The numbers here are staggering.
Oh, they are hard to even wrap your head around.
I read they could form almost 10 billion stars in just 10 million years.
Yeah. If we connect this to the bigger picture, you're looking at an environment with immense reservoirs of gas collapsing under a huge gravitational pull.
So the ceiling is totally lifted.
Exactly. The macro environment, the massive galaxy, allows for millions of these ultra-bright, massive stars to form.
Okay, wait, here's where it gets really interesting, though. Let me push back on this a bit.
Sure.
If a dwarf galaxy is still made of the same fundamental stuff, the same gas, why couldn't it just get lucky one day?
What do you mean?
Like, why couldn't the gas inside a dwarf galaxy just randomly clump together in one specific spot against the odds to make just one single ultra-bright star? If it's all random probability, shouldn't there be an outlier?
And that exact assumption that it's just a matter of getting lucky is exactly what the scientific community used to believe.
That the curve just kept going.
Right. They thought a dwarf galaxy just had fewer rolls of the dice, so it was less likely to form a giant star, but technically still possible.
But it's not.
No, it's not. And we finally got the proof of that in 2006.
This was the major discovery by Professor Pavel Krupa and Karsten Widener, right? Over at the University of Bonn.
Yes. They actually tested this assumption. And what they discovered completely broke the cosmic lottery idea.
What did they find?
They found that the mass of the single most massive star in any given cluster is strictly mathematically determined by the total mass of the star cluster itself.
Strictly determined, meaning no random chance.
Zero. It's a profound philosophical shift. We went from a paradigm of chance to a paradigm of pure determination.
I mean, we really have to praise Krupa and Widener here for challenging that consensus. It takes a lot to look at a universally accepted idea like the universe is random and say, actually, the math says otherwise.
It's crucial in science to question those foundational assumptions. And they proved that the stars aren't forming in these isolated random little bubbles.
They are deeply connected to the larger environment.
Right. Krupa developed this concept called optimal sampling.
Optimal sampling. Okay, explain that for us.
Basically, he calculated that the masses of stars in a cluster aren't pulled out of a hat at random. They follow a precise mathematical order. There is absolutely no room for statistical fluctuations.
Wow. So it's like baking a cake.
Okay, I'm following.
You don't just randomly end up with a huge 5-tier wedding cake if you only have a tiny little mixing bowl.
Exactly.
The size of the bowl, which is our star cluster, strictly dictates the maximum size of the cake, the star. And it does it with absolute mathematical precision. No random miracles allowed.
That is a great way to look at it. The limits are hard-coded into the environment.
But wait, a gas cloud spanning 50 light years doesn't have a brain. It doesn't know how big its mixing bowl is, right?
Right. It's just gas and physics.
So Krupa and Widener proved that this strict, self-regulating order exists. But for years, physicists were totally stumped on why, right? Like, how is the universe actually pulling off this calculation without a central computer?
That was the missing piece. We had the empirical proof that it was happening, but we didn't have the underlying mechanism until very recently.
Enter Dr. Ida Gergo from Nanjing University.
Yes, she finally solved the why. And she did it by bringing in a concept that you usually don't hear in astrophysics.
Which is Shannon entropy.
Right, information entropy.
Okay, let's slow down here because applying information theory to giant burning balls of gas is pretty wild.
What's fascinating here is that Shannon entropy is essentially a way to measure the efficiency of information distribution. And Dr. Gergo proved that a star cluster develops according to a uniquely efficient principle.
So out of all the chaotic, infinite ways the gas could randomly clump together to form stars, the universe just chooses one.
Not just any one. It chooses the path of least resistance. Out of all the theoretically possible mass distribution scenarios, The one that naturally plays out is the one that maximizes the Shannon entropy.
Meaning it's the most mathematically natural state.
Exactly. It's the state that is the most robust on a large scale and the least dependent on messy microscopic details.
Okay, so it's like predicting how a massive crowd of people is going to exit a sports stadium, right?
That's a perfect analogy. Go ahead.
Like, you don't need to know the microscopic details of every single person in that stadium. You don't need to know their mood or their exact walking speed or if they stop to tie their shoe.
Right, because that's just microscopic noise.
Exactly. If you just look at the large scale, like the width of the exit doors and the total number of people, you can predict exactly how the crowd will distribute itself flowing out of the building.
Because the crowd will naturally just follow the most efficient flow.
The universe is just ignoring the chaotic details of every single gas atom and focusing purely on the large-scale natural balance.
Yes. The universe basically doesn't waste energy on chaotic, random distributions when a highly efficient, mathematically natural state is right there. It's an incredibly efficient, self-regulating process.
That is just so elegant. So what does this all mean for the researchers? If the universe is doing all this hyper-efficient organizing for us, how does that change the day-to-day work of an astrophysicist?
It changes absolutely everything. I mean, it takes incredibly complex, chaotic math and basically boils it down to a single magical number.
Just one number.
One number. Because of this discovery, all our old theories about star populations are being entirely reformulated.
Because the old way was a nightmare, right?
Always a computational nightmare. Previously, if you wanted to run an evolutionary model of a galaxy, you had to account for random chance.
Which meant rolling the dice thousands of times.
Millions of times, really. You had to use these massive supercomputers to perform thousands of random stochastic calculations just to guess what a single star cluster might look like. Now, researchers only need one number: the total mass of the star population.
Wait, really? Just the mass?
Just the mass. You plug that one number in, apply the entropy principles, and you instantly know exactly what kinds of stars and how many of them will form from that gas cloud.
No more rolling virtual dice?
No more rolling dice. The math is highly efficient now.
I mean, just think about the hidden physical cost of the old way. We're talking about supercomputing time. Massive servers running hot, eating up electricity, trying to simulate random chance.
By removing the need for all those random calculations, this discovery is literally saving massive amounts of electrical energy and computing power on Earth right now.
It's just wild to me, the idea that you can look at an unimaginably vast cloud of gas thousands of light years away, measure its mass, and instantly have the exact inventory of stars it will produce.
It is deeply satisfying from a physics standpoint.
But it's not just about saving electricity on Earth, is it? This new mathematical certainty actually forces us to rip up the textbooks and rewrite our understanding of how matter cycles through the universe.
Oh, absolutely. A whole host of calculations on the evolution of galaxies will now need to be completely redone.
Because of the dwarf galaxies.
Because of the dwarf galaxies. Remember our fundamental takeaway. Contrary to those old theories, small dwarf galaxies absolutely do not form any massive stars.
Zero.
Zero. And that fundamentally impacts the theory of the matter cycle in the universe.
Okay, let's break down that matter cycle for everyone, because massive stars are really the engines of the universe, right?
They are the ultimate foundries. They live fast, they die hard in these massive supernova explosions, and when they explode, they seed the universe with heavy elements.
Things like oxygen, carbon, iron, the stuff we are made of.
Exactly. But if a dwarf galaxy never produces these massive stars,
then a dwarf galaxy never has those supernovas.
which means they play a completely different role in the cosmic ecosystem than we previously thought. They aren't seeding the universe with those same heavy elements.
They're just sitting there hoarding their hydrogen in those little nightlight M-dwarfs.
Basically, yeah. So a large number of small molecular clouds just cannot do the heavy lifting of one very large cloud.
The universe's heavy lifting is exclusively done by the big players, the massive ellipticals and spirals.
Right. And as Professor Ziyu Zhang, one of the co-authors of the study, pointed out, this is going to lead to entirely new observation projects.
We have to look at the sky with a completely new lens now.
We do. We have to specifically study this non-random formation. It changes our entire roadmap for observing deep space.
You know, this raises a really important question for you, the listener. Just think about how many times in science we assume something is random purely because we don't yet understand the rules governing it.
That happens all the time. We mistake our own lack of a formula for genuine chaos.
Exactly. We see a messy gas cloud and assume the universe is just throwing darts at a board. But really, it's executing this flawless, hyper-efficient mathematical equation.
That's humbling, really.
It truly is. So just to quickly recap this incredible journey we've been on, we started from this long-held assumption of the cosmic lottery.
The idea that it was all just random chance.
Right. Then we moved to Krupa and Widener, who discovered that cluster mass actually places strict, non-random limits on star size.
Proving that the lottery was totally rigged.
Exactly. And finally, we arrived at Dr. Jirgo's brilliant realization that the universe uses Shannon entropy information theory to perfectly and efficiently self-regulate star birth.
Fundamentally changing how we calculate the evolution of entire galaxies.
It is just a massive leap forward, and it leaves us looking at the night sky not as this random, chaotic scattering of light, but as a perfectly balanced equation.
And, I think that leads to a really profound thought to walk away with.
Oh, absolutely. What are you thinking?
Well, if star formation, which is arguably one of the most violent, massive, and seemingly uncontrollable processes in the universe, is actually governed by the most efficient, mathematically natural distribution possible, what other seemingly chaotic systems out there are secretly doing the exact same thing? Whether it's in the cosmos or even in our everyday lives, what other massive, unpredictable systems are secretly masking a perfectly efficient mathematical order, just waiting for us to discover that one single number?
Oh, wow. That is a brilliant question to end on. I love that. A hidden blueprint waiting in the chaos. Well, that is definitely something to mull over. We hope you've enjoyed this exploration and that it encourages you to keep looking up, keep asking questions, and maybe give the universe a little more credit for its organizational skills. Thanks for joining us, and we'll catch you next time.